Okay, imagine this. The dusty red plains of Mars stretch out before you. But before any human boot touches that alien surface, robots are already there, tirelessly working.
Hmm.
Not just simple rovers rolling over rocks, but sophisticated machines, thinking, deciding, building, even setting up the very foundations of a future human base miles and miles away from Earth.
Yeah, it's a pretty wild image.
Or picture an astronaut deep in the unforgiving black of space facing a sudden life-threatening emergency, a critical system failure, perhaps.
Okay.
Instead of panicking or waiting agonizing hours for delayed communication with Earth, an intelligent AI companion is right there, accessing vast knowledge bases, offering real-time diagnosis, recommending solutions, maybe even guiding the astronaut step by step through a complex repair or medical procedure.
It absolutely sounds like science fiction, doesn't it? Like the kind of advanced technology we've only seen in movies. But what the sources make clear is that this isn't just a far-off fantasy anymore. It's the rapidly approaching reality of space exploration, and it's becoming, well, essential for our most ambitious goals, like getting humans to Mars and keeping them alive there.
Exactly, and that's what we're diving into today. The incredible, accelerating role of artificial intelligence in pushing humanity's reach farther and farther beyond Earth.
Hmm.
We're specifically going to unpack the exciting, sometimes sci-fi sounding concept of AI astronauts. Not necessarily just robots that look like us, but intelligent agents that can perform roles we typically associate with human crew members, and how they're becoming absolutely crucial for making those plans for Mars, particularly in the coming decades, actually happen.
And for this deep dive, we've pulled together a stack of sources specifically for your understanding, a mix of cutting-edge research papers, official reports from space agencies around the world, and recent news articles covering the latest developments.
Yeah, quite a pile of reading.
Definitely. Our mission is to sift through all that material, extract the most important nuggets of knowledge, and give you a shortcut to being truly well-informed on this cutting-edge field.
Think of us as your guides to this fascinating material. What is AI already doing in space right now, today?
Good question.
What is the actual vision for these so-called AI astronauts? And what incredible technological leaps are still required to get there? How exactly might they be involved in exploring and settling Mars in the 2030s and 2040s, the decades we're targeting for human footsteps?
And the big questions, too.
And of course, what are the significant advantages they offer, the tough technical challenges we still need to overcome, and the really critical ethical and policy questions that come with sending increasingly intelligent machines on these interplanetary journeys?
It's a field buzzing with intense activity and innovation across the globe. Every major space player, from national agencies, like NASA and ESA, to private companies reshaping the industry, is investing heavily in this technology.
Everyone wants a piece of this.
Oh, yeah. It's genuinely thrilling to explore just how quickly things are evolving and what it means for our future among the stars.
Absolutely. The implications for the future of humanity living and working beyond Earth are massive. So let's get started by grounding ourselves in the present.
Okay, let's unpack this.
Right. Let's move from that broad, exciting introduction to the ground truth. AI isn't just some far-off dream. It's a critical part of space missions today.
Yeah, it's already working.
It's not just coming, it's here, working among the stars as we speak,
Yeah.
enabling operations that would be impossible otherwise.
That's profoundly true. According to the sources, AI technologies are already deeply embedded and, frankly, indispensable in modern space activities.
Indispensable is a strong word, but it sounds right.
It is. They allow spacecraft and robots to operate with far greater autonomy and intelligence than ever before, fundamentally transforming how we conduct operations in space, especially as we venture further from Earth.
And the sources break this down into a few key domains where AI is currently making a real, tangible difference right now. The first is in space robotics and autonomous systems. This is perhaps the most visible area to the public.
Yes, and we see this prominently both on the International Space Station and on planetary surfaces. On the ISS, AI is powering a new generation of free-flying robotic assistants.
Like those little cubes.
Exactly. Take NASA's Astrobee cubes, for example. These are cube-shaped robots named Honey, Bumble, and Queen that use electric fans to maneuver freely in microgravity. They assist with routine tasks like monitoring inventory, taking photos for ground control, or even assisting with crew experiments by acting as a stable camera platform or carrying equipment.
So they're like little helpers buzzing around.
Pretty much.
Mm.
And the Isadel Simon sphere is another example. Simon is a floating robot with a screen face that acts as an autonomous helper. These free flyers are essentially mobile cameras, sensors, and assistants that can operate underground control or autonomously.
And crucially, they're test beds, right?
Yes, importantly, they are being used as test beds for the kind of zero-G robotics and complex human-robot interaction that will be absolutely vital for future missions to the Moon and Mars. They're proving the concept of a mobile, intelligent assistant working alongside humans in space.
Makes sense. Proving it out in orbit first.
On planetary surfaces, the AI role is even more critical because of the sheer distance and resulting communication delays. Robotic landers and rovers simply must rely heavily on AI to perform tasks without constant real-time human control.
Right, you can't joystick them from Earth.
Not effectively. The sources highlight NASA's Perseverance and Curiosity rovers on Mars. They use sophisticated onboard AI systems for autonomous driving and hazard avoidance.
And you mentioned why this is necessary. The communication delay from Earth to Mars is significant, anywhere from, 6 to 40 minutes round trip, depending on orbital positions?
That's right. You just cannot joystick a rover live the way you would a drone on Earth. So the robot needs to be able to see a hazard, like a large rock, a steep drop-off, or unexpected soft sand, and decide how to avoid it itself in real time.
In milliseconds.
Exactly. Milliseconds, not minutes.
So these rovers are operating in these, incredibly extreme and unpredictable environments. They're precursors. Helpers for future humans.
Precisely. They serve as crucial precursors and helpers for future human explorers, carrying out routine or risky activities that pave the way. They are autonomously conducting the initial reconnaissance and site surveys that future astronauts will build upon.
Which leads us right into the next key domain where AI is fundamental, autonomous navigation. This applies not just to rovers driving on a surface, but to spacecraft moving through the cosmos.
Absolutely crucial for rovers and spacecraft alike. Perseverance's enhanced autonav is a prime example of just how far this has come. It uses advanced machine vision, essentially giving the rover eyes that can understand the terrain.
So it sees the path ahead.
It sees it, maps the area ahead, identifies obstacles, and plans safe, optimal routes, all while making real-time decisions without waiting for commands from Earth. This capability allows Perseverance to drive much faster and cover significantly more ground than previous rovers, dramatically increasing the area it can explore in a given time.
And it's building on earlier foundational work, right?
Yeah.
The oldest Spirit and Opportunity rovers pioneered autonomous hazard avoidance, but the newer systems are performing navigation and route planning at a whole new level of sophistication and speed.
Correct. Another key piece of AI for autonomous navigation on Mars is AGIS, the autonomous exploration for gathering increased science software used on both Curiosity and Perseverance.
AGIS sounds cool. What does it do?
AGIS uses AI to analyze camera images, identify scientifically interesting targets like particular rocks or soil textures based on criteria set by scientists on Earth. It can then automatically direct the rover's instruments, like its camera mast or spectrometer, to collect data on these targets.
So it's like having a junior geologist on board, scanning the landscape and saying, hey, that rock looks interesting. Let's zap it with a laser or something.
Exactly. That's a great way to put it. This maximizes science return, ensuring valuable observations aren't missed while the ground team is offline or busy processing data from other activities. It significantly increases the scientific output the rover can achieve each day.
And AI is vital not just for driving around, but for the incredibly complex task of getting there in the first place, autonomous landing systems. Landing precisely and safely on a rocky, unknown surface like Mars is one of the hardest things we do in spaceflight.
It truly is one of the biggest nail-biters. Achieving safe, precise landings on other worlds requires highly autonomous guidance. Systems using AI, including terrain relative navigation and hazard detection LiDARs, that's LiDAR, L-I-D-A-R, which uses pulsed lasers to create detailed 3D maps of the surface in real time.
Okay, so it's mapping as it lands.
Yes, it compares this real-time sensor data to onboard maps to identify safe landing spots and adjust the landing trajectory on the fly to avoid hazards like big rocks or craters. This was dramatically demonstrated by the Mars 2020 Entry, Descent, and Landing System, nicknamed 7 Minutes of Terror, when it used AI to put Perseverance down safely in a challenging area.
I remember watching that landing. Tense stuff. So whether it's driving on the surface, selecting science targets, or performing the critical landing phase, AI is enabling operations that would be either impossible or severely limited by those long communication delays to Mars. It's not an optional extra, it's absolutely vital.
That's the bottom line. Another important area is decision support systems. Here, AI isn't necessarily a physical robot, but acts more like a virtual crew member or a super intelligent ground assistant.
Like an intelligent co-pilot in the cockpit, or a helpful librarian who knows absolutely everything in the spacecraft's manuals.
Exactly. NASA has prototypes like the astronaut agent, which is under development through their SBIR program, the Small Business Innovation Research Program.
SBR, right? They fund new tech from smaller companies.
Yeah, designed to explore promising new technologies. This agent is envisioned as a voice-activated AI assistant to help astronauts run spacecraft systems, detect anomalies by cross-referencing sensor data and system parameters, and pull up relevant information instantly. The core idea is to improve crew autonomy by providing information and guidance without constant ground support or relying on bulky paper manuals.
And Simon on the ISS, powered by IBM Watson, is already doing some version of this. It can converse with astronauts, retrieve information from digital manuals and procedures databases, and guide them through tasks hands-free.
The sources mention it aims to provide advice and information, freeing the crew from needing to contact Earth for routine queries or checks, or having to look up information manually while their hands are busy.
Keeping astronauts focused on the task, not the manual.
Precisely. And it's not just for the astronauts on board. Ground operations benefit immensely, too. ESA, for example, is testing large language model assistants for flight controllers.
Like a ChatGPT for mission control.
Sort of, yeah. Allowing them to query vast amounts of complex spacecraft documentation and operational procedures in plain language, getting immediate, relevant answers. NASA's ASPEN and Class P systems also use AI to analyze mission constraints and optimize complex mission plans and schedules, finding the most efficient way to sequence activities for a spacecraft or rover.
That makes perfect sense. Managing the sheer volume of data and complexity of a deep space mission requires incredible coordination and analysis, and AI can help untangle that complexity, making operations more efficient for both the crew in space and the teams on the ground.
Moving on, AI is also essential for data processing and scientific analysis. Space missions, especially those with advanced instruments, generate enormous volumes of raw data images, sensor readings, spectral data. Bandwidth back to Earth from deep space is always limited.
Right, you can't just send everything back. So AI helps make sense of this fire hose of information and prioritize what's most important to send home.
Yes. Onboard AI algorithms can prioritize and pre-process data before transmission, often compressing it or flagging critical findings. A great example is the ESA's upcoming Rosalind Franklin Mars rover, part of the ExoMars mission, though it's been delayed.
Ah, yes, the rover with the drill.
That's the one. It will use a NASA-provided machine learning algorithm in its onboard analytical lab called MUMA to rapidly identify organic molecules in drilled soil samples.
That's a fascinating use of AI for science.
Yeah.
It's analyzing the data right there on...
Exactly. This allows the rover to quickly flag scientifically interesting chemistry, enabling scientists on Earth to make quicker decisions on follow-up analysis or drilling locations without waiting days for lengthy raw data transmission and processing back on Earth. It significantly speeds up the pace of scientific discovery on another planet.
Very cool. Getting faster science done.
And we see this trend on Earth observation satellites, too. ESA's SAT-1, launched in 2020, used an AI chip to filter out cloudy images before downlinking, so only the useful, clear data was sent, saving valuable bandwidth and processing time on the ground.
Smart. Don't send the useless pictures.
Pretty much. The trend is clearly towards moving this intelligence closer to the data source onto the spacecraft itself for faster insights and more efficient use of limited resources, which is absolutely critical for deep space missions where bandwidth is a precious resource.
Makes total sense. Finally, AI is playing a big role in onboard diagnostics and health monitoring. Keeping complex spacecraft systems running smoothly, especially on years-long journeys or during crewed stays, is absolutely vital, and AI can help spot problems early before they become catastrophic.
Precisely. Spacecraft are increasingly equipped with AI for autonomous fault detection, diagnosis, and even recommending repair steps or suggesting workarounds. NASA pioneered this concept decades ago with the Livingstone software on the Deep Space One probe.
Deep Space One, that was back in the late 90s, right?
Yes, it successfully tested automatic detection and response to simulated failures in its own systems, way ahead of its time.
So the spacecraft can essentially notice something is wrong with itself and potentially figure out what it is and maybe even how to fix it, or at least suggest a fix.
That's exactly the goal. On the ISS and modern satellites, AI systems constantly monitor life support, power distribution, propulsion, and other critical systems, looking for subtle anomalies that might indicate a developing problem.
Catching things humans might miss.
Or catching them much faster. They alert crews or ground control to these issues, often much faster than human monitoring alone could. The ISS's Smart Electrical Power System, for example, uses AI to analyze data and predict potential power failures before they happen. ESA's new AI lab, established in 2024, is focusing heavily on advanced anomaly detection techniques for future deep space missions.
The vision is for spacecraft to be increasingly capable of self-diagnosis, identifying an issue like a minor leak, a computer glitch, or a power fluctuation, and either fixing it themselves through system reconfiguration or providing the crew with clear, step-by-step recommended actions.
Which is crucial when ground contact is delayed or completely unavailable.
Yeah, you're on your own out there.
And the sources also specifically mention medical diagnostics for crewed missions, AI virtual doctors using data from astronaut wearables and health sensors to analyze physiological data and provide medical decision support on those long, isolated Mars missions.
Wow, an AI doctor in space.
It could range from suggesting a course of treatment for a minor ailment to guiding an astronaut through performing complex procedures in an emergency.
That's a critical safety net when medical expertise from Earth is literally minutes or even tens of minutes away. AI-driven diagnostics significantly improve the safety and resilience of these systems by catching issues early and helping both automated systems and human operators respond effectively.
So to summarize this first section, AI is not just a future concept. It's already deeply embedded across almost every facet of space exploration today. It's driving rovers across Mars, flying satellites autonomously, assisting astronauts with procedures, processing vast amounts of scientific data on board, and monitoring the critical health of spacecraft systems.
Yes, the sources consistently describe AI as indispensable for future exploration, enabling levels of autonomy and efficiency that simply weren't possible before. They clearly view the current state as a fundamental, necessary stepping stone towards the even more capable systems envisioned as AI astronauts in the near future. The examples like Astrobee and Simon aren't just interesting gadgets. They are concrete research testbeds, explicitly sharing the goal of developing the technologies needed to support crew operations for those future Mars missions.
That gives us a great baseline, showing AI is already doing a lot of heavy lifting. But who is leading the charge to build the more advanced systems that are starting to fit this description of AI astronauts? Let's look at the major agencies and companies mentioned in the sources and see what specific projects they're pursuing.
It's truly a global effort, isn't it? Leading national agencies and a rapidly growing number of private companies are all investing heavily in AI-driven robotics and autonomous systems, each with slightly different focuses and approaches, reflecting their unique goals and capabilities.
Let's start with NASA, the United States agency, which you'd expect to be a major player given its long history in both human and robotic spaceflight. They have quite a diverse portfolio in this area.
They certainly do. On the human spaceflight side, they've experimented with humanoid robots like the Robonaut series. Robonaut 2, or R2, was the first dexterous humanoid robot on the ISS, designed to assist astronauts with tasks inside the station.
I remember R2. Looked pretty cool.
Yeah. While initially teleoperated, it showed the potential for complex manipulation in microgravity using a human-like form factor.
And then there's Valkyrie, R5. This prototype is much larger, standing 1.9 meters tall, and really looks the part of a potential future AI astronaut in a spacesuit.
Valkyrie looks imposing.
It does. NASA and its research partners envision sending robots like Valkyrie to Mars before humans even arrive.
So basically getting the habitat ready, building things like landing pads or setting up power systems, performing initial site surveys, doing the crucial, often dangerous prep work so humans can focus purely on exploration and science when they finally land.
Exactly. The sources call this concept of robotic precursors and helpers, leveraging advanced AI and teleoperation, a cornerstone of NASA's Moon to Mars strategy. During a crewed mission, robots like Valkyrie could also handle routine maintenance, repairs, or complex external operations like spacewalks, known as EVAs.
Taking the risk away from the humans.
That's a big part of it. Beyond humanoids, NASA has the free flyer robots on the ISS we mentioned, the Astrobee system, Honey, Bumble, and Queen.
The cubes again?
Yeah, these small cube-shaped robots serve as inventory scanners, mobile cameras, environmental sensors, and test beds for zero-G robotics, and how humans and robots will interact and cooperate in future habitats. They are explicitly designed to offload routine tasks from astronauts.
And they tested Callisto on Artemis the First, the uncrewed Orion capsule that flew around the moon. Callisto was a tech demonstration involving a voice-activated AI integrated into the cabin.
A collaboration with Lockheed Martin, Amazon, and Cisco, right?
That's it. This system used commercial AI technologies, like adapted Alexa and WebEx, to respond to verbal commands, query a local knowledge base on board the capsule, and provide information to astronauts in deep space, showcasing how commercial AI could support crews on those long, isolated journeys without relying on constant Earth communication.
So testing how commercial AI could support crews on those long deep space missions, very practical.
Right. For planetary exploration, NASA's Mars rovers are the flagship examples of AI autonomy in action. Curiosity introduced AG Kizil-Ass for autonomous science target selection, significantly increasing science return. Perseverance advanced this with enhanced AutoNav.
Allowing it to drive much faster and cover more distance autonomously while detecting and avoiding obstacles in real time. A huge leap in capability.
And Ingenuity, the Mars helicopter that flew with Perseverance, relies entirely on onboard vision and an AI-based navigation filter for its autonomous flights.
Yeah, the little chopper that could. It acts as an AI-powered aerial scout for the rover, demonstrating autonomous flight on another planet. Just amazing.
The upcoming Mars sample return campaign will also be highly autonomous, featuring a fetch rover or drone that autonomously navigates to pick up sample tubes left by Perseverance and an ascent vehicle that autonomously launches those samples to orbit.
These are unprecedented levels of autonomous operations on another planet for sample collection and launch. A really complex ballet of robots.
And looking beyond Mars, the planned Lunar Gateway Station, orbiting the Moon, is designed with significant autonomous maintenance capabilities for when crews are absent.
And NASA is even considering AI caretaker software for lunar habitats between visits, ensuring systems stay operational, like a smart home system for the moon base.
So NASA's efforts clearly span the spectrum, from humanoid robots for future construction, to ISS assistants supporting crew and testing HRI, to highly autonomous planetary explorers. All are explicitly described as building blocks for crewed Mars missions.
Moving to Europe, ESA, the European Space Agency, and the German Aerospace Center, DLR, have some notable projects, particularly focused on AI companions and exploration autonomy.
And the most famous one is probably Simon, the crew interactive mobile companion, that floating sphere with the smiley face.
Yes, developed by DLR and Airbus, powered by IBM Watson AI. Simon flew on the ISS on 2 missions, Simon 1 and Simon 2, designed to be a hands-free conversational assistant. It understands voice commands, retrieves information from digital manuals, displays procedures, and can even engage in basic social chat.
I remember reading that a core idea behind Simon is to evaluate how an AI companion could potentially reduce stress and workload for astronauts on long missions, perhaps even providing psychological support. It even conversed in German with astronaut Alexander Gerst during some of its tests.
Exactly. ESA plans to develop these AI companions further, aiming for systems that can not only provide technical support but also understand human emotion and social cues to offer more meaningful psychological support over years-long journeys to Mars.
It's a fascinating and maybe slightly creepy direction. A robot that knows how you're feeling. On the robotics side, for planetary exploration, ESA's Rosalind Franklin Mars rover, part of the ExoMars program, though delayed to 2028, is designed with significant AI capabilities.
It will have autonomous navigation similar to NASA rovers, but uniquely, it will use a machine learning algorithm from NASA's MoMA instrument in its onboard lab to rapidly analyze drilled soil samples for organic molecules.
So using machine learning for science right there.
This makes it one of the first interplanetary missions to use AI for rapid onboard scientific discovery on another planet, allowing scientists to make quicker decisions on what samples are most interesting for deeper analysis or collection.
That's a powerful application of AI speeding up the scientific process right there on the surface of Mars.
ESA is also exploring advanced AI concepts through its new ESA AI Lab established in 2024, integrating AI into astronaut training with VR simulations, developing spacecraft digital twins for predictive maintenance, and researching radiation-hardened AI hardware suitable for deep space.
Digital twins, so like a virtual copy of the spacecraft.
Exactly, that the AI can monitor and run simulations on. They even conducted the Analog 1 experiment in 2019, where an astronaut on the ISS remotely controlled an AI-powered robotic arm on Earth in a Mars analog environment for sample collection, showcasing how humans and AI can cooperate effectively over long distances with AI providing essential, real-time assistance.
And they have AI in satellite operations too, like the Sat-1 filtering cloudy images. So ESA's focus includes exploration autonomy with rovers and analog tests, as well as crew support AI with Simon and future companions.
Japan's space agency, JAXA, has made unique contributions, particularly in the area of human-robot interaction and practical in-space helpers.
Kirobo, the little talking robot astronaut from 2013, is probably the most famous early example.
Yes, Ikuribo was a small android that conversed with astronaut Koichi Wakata on the ISS. It was a pioneering project in social robotics in space, demonstrating how robots might potentially help with psychological support and loneliness on long-duration missions, even if its AI capabilities were limited compared to today's systems.
A little friend in space. And they also developed the very practical InBall, the spherical camera drone on the ISS.
IntBall, introduced in 2017, was a spherical camera drone that could be remotely piloted or follow pre-programmed paths inside the Kibo module. Its primary purpose was to give ground control eyes inside the station without requiring an astronaut to operate a camera, saving valuable crew time.
Just freeing up the astronauts' time.
Exactly. The upgraded IntBall 2, tested recently, has more autonomy, including the ability to navigate and dock itself to a charging station, further reducing mundane tasks for astronauts and increasing efficiency.
Looking ahead, JSA's is collaborating with Toyota on the Lunar Cruiser rover for Artemis missions, which includes autonomous driving and route planning capabilities for lunar exploration.
A car company helping build a moon rover makes sense.
They are also contracting companies like JAXA to test robotic arms and small rovers for future habitats and surface operations, like the tests JAXA has conducted inside and outside the ISS, demonstrating assembly and maintenance tasks in vacuum.
So, Japan is focused on interactive robotics and developing practical autonomous devices to serve as reliable helpers in space habitats and for future surface missions, emphasizing human-robot collaboration to offload tasks.
Russia's space agency, Roscosmos, has experimented with humanoid robots as well, most notably Skybot F-850, also known as Fedor.
Skybot F-850 was a humanoid robot sent on an uncrewed Soyuz mission to the ISS in 2019. Cosmonauts on the station teleoperated it to perform simple tasks inside the module, like flipping switches and connecting cables. This was primarily a test of the humanoid hardware's performance in microgravity and the teleoperation systems.
So while the hardware was capable of human-like movements, it wasn't truly autonomous. It was being remotely controlled by a human astronaut, more like a remote puppet.
Correct. More of an avatar. However, its designers estimate that a fully autonomous AI cosmonaut capable of independent work could be developed in the next 10-15 years with sufficient investment, potentially ready for use by the early 2030s. They have concepts for using future humanoids for hazardous lunar and Mars work ahead of human arrival, similar to NASA's Valkyrie Vision tasks, too dangerous for humans initially.
And Russia is also collaborating with China on plans for autonomous robotic-based construction on the Moon in the 2030s as part of the nascent International Lunar Research Station concept,
which will start as a robotic outpost. So Russia's contributions include early humanoid teleoperation demonstrations and joint plans for robotic infrastructure deployment in deep space.
China's National Space Administration, CNSA, has made rapid progress in space exploration and is increasingly incorporating AI, particularly with their successful autonomous rovers.
Yes, there's Zhurong Mars rover from the Tianwen-1 mission, which successfully landed on Mars in 2021, is a prime example. It used autonomous navigation and hazard avoidance capabilities, along with AI vision algorithms for terrain classification and target detection, allowing it to plan its own routes and operate independently for significant periods.
Zhurong successfully navigated complex terrain, avoided obstacles, and performed its scientific mission using its onboard autonomy. Quite an achievement.
China's long-term roadmap for Mars exploration, unveiled in 2025, is also highly significant in terms of AI. It includes establishing a fully robotic Mars research station by 2038.
An uncrewed robotic base focused on in-situ resource utilization and research explicitly as a precursor to human missions, building the groundwork.
Exactly. This robotic base would likely involve swarms of AI-controlled robots for tasks like digging ice from the Martian subsurface, generating oxygen from the atmosphere, and possibly 3D printing habitats using local materials.
Wow, robots building houses on Mars.
The goal is explicitly to prepare Mars for eventual human arrivals in the 2040s by establishing basic infrastructure and proving key technologies like ISRU, in situ resource utilization. It mirrors their lunar strategy, with the ILRS starting as a robotic base. On their Tiangong space station, they use robotic arms with AI-based vision for guidance and positioning, reducing the need for astronauts to perform risky or time-consuming external activities.
So China is focusing on proven autonomous rovers and leveraging AI for self-reliance in planned robotic outposts, along with developing capabilities in areas like satellite swarm coordination and intelligent fault diagnostics for their growing space assets.
Finally, the private sector, encompassing companies like SpaceX, Blue Origin, and others, is making major strides using AI, primarily to automate and streamline spacecraft operations, which is critical for reducing costs and increasing reliability.
SpaceX's Crew Dragon is a fantastic example of this. It's been routinely ferrying astronauts to the ISS since 2020, and its entire flight profile, from launch insertion and orbital maneuvering to rendezvous and docking with the ISS, is fully autonomous using AI-driven guidance, navigation, and control GNC systems.
GNC, right, the brain of the spacecraft.
Yes, the complex software and hardware that figures out where a spacecraft is, where it needs to go, and how to get it there.
Yes. The Demo 1 mission in 2019, the uncrewed test flight, was the first autonomous U.S. docking with the ISS, showcasing the maturity and reliability of this AI technology. Automating these critical phases reduces human risk and training requirements significantly.
Less for the astronauts to worry about during those critical moments.
Exactly. SpaceX is applying the same philosophy to Starship, their next-generation vehicle designed for transporting large numbers of people and cargo to the Moon and Mars, which is being designed for largely autonomous flight profiles and complex propulsive landings, like their Falcon 9 rockets, which also use AI-driven GNC for landing.
Elon Musk has even speculated publicly about uncrewed Starship landing attempts on Mars, needing extremely robust autonomous guidance to identify safe landing zones and execute the final descent without human input. These rockets and capsules are essentially AI pilots.
Blue Origin also uses highly automated, AI-driven guidance systems in their suborbital New Shepard and orbital New Glenn rockets. And their lunar lander proposal for NASA includes an AI-powered hazard detection system using machine vision during the descent phase to identify safe landing spots.
Everyone's using AI for landings now, it seems.
It's becoming standard practice for precision landing. And beyond launch vehicles and capsules, there's a whole ecosystem of startups and established companies growing in the in-space services sector, heavily leveraging robotics and AI.
Right. Companies like pAI, which we mentioned with JAXA and Olivian, are developing advanced robotic arms and crawlers specifically designed for assembly, maintenance, and repair tasks in space.
And Northrop Grumman's MEV-1 mission in 2021 was the first commercial autonomous orbital servicing mission, demonstrating a satellite robot docking with and extending the life of a commercial satellite, fixing satellites in orbit autonomously.
And looking specifically to Mars, private firms might provide specialized robots for specific tasks. Imagine adapting Boston Dynamics legged robots for scouting or carrying equipment.
Spot the dog on Mars.
Right, or deploying off-world industrial mining robots powered by AI for in-situ resource utilization on a massive scale.
Yes. SpaceX's vision of a Mars colony could potentially involve dozens or even hundreds of cargo starships landing on Mars, each unloading AI-powered autonomous machines, perhaps what some might call an AI robot army.
An AI robot army, okay.
To rapidly bootstrap infrastructure like power generation, propellant production, and habitat assembly before any humans arrive.
So the commercial sector's embrace of AI for automating spacecraft operations, developing service robots, and potentially enabling rapid Mars base buildup is indispensable for Mars, significantly increasing safety and lowering costs where human intervention is either impossible or too risky due to the distance and environment.
So that's a really comprehensive global snapshot of what's happening today and what's being actively developed. We see national agencies pushing boundaries with humanoid robots, AI companions, and autonomous explorers, while private companies are leveraging AI to make spaceflight more routine and envisioning AI-powered robotic workforces on other planets.
And all of this investment, research, and development builds towards a larger integrated vision, the concept the sources are starting to call the AI astronaut.
Let's dive into that. What do the sources mean by AI astronaut? It sounds like something pulled straight from science fiction, maybe like data from Star Trek, but it's described as being more about function and intelligence than necessarily looking like a human, right?
Exactly. The sources define AI astronaut as essentially a shorthand for highly intelligent, autonomous agents, which could be robotic, entirely virtual like advanced software, or a hybrid that can perform complex roles typically expected of human astronauts.
So not just a metal man.
No, it's not limited to just humanoid robots. It encompasses advanced AI software embedded in spacecraft capable of independent decisions, sophisticated digital assistants that act like crewmates, or intelligent robots of various forms capable of operating with minimal human oversight.
The core idea seems to be about extending human capabilities in space by using machines that can think, learn, and act with a significant degree of independence and cooperation. The goal is to enhance mission success, dramatically improve safety, and enable exploration that would otherwise be impossible.
And the sources are clear that while we have systems today that are the closest we've come, like Simon or the astronaut agent prototype, they're still quite limited compared to the science fiction ideal of a fully capable AI crewmate.
Right. Things like Simon are interactive and perform specific limited tasks. Simon is described as a flying brain that can provide information and guide procedures, acting like a friendly colleague.
The smiley face helps.
It probably does. But it's still far from human-level adaptability, common sense, or problem-solving across a wide range of unexpected scenarios.
And while robots like Valkyrie have incredibly advanced hardware with human-like dexterity and mobility, engineers developing them note they still need vastly improved AI software to reliably perform complex tasks off-leash on their own in an unpredictable environment.
The brain needs to catch up with the body, basically. And Fedor, as we discussed, was largely teleoperated, acting as more of a remote avatar than an independent crew member.
So the gap between current capabilities and a true, highly functional AI astronaut capable of operating independently or as a seamless human team member is significant, and bridging that gap requires several major technological leaps described in the sources.
The first, and perhaps most critical one the sources highlight, is achieving true autonomy in unstructured and unpredictable environments.
Handling the unexpected, that sounds like the big one.
This is a fundamental challenge for any AI operating in deep space. Space is inherently unpredictable. Unexpected dust storms, sudden equipment failures, traversing complex, unknown terrain, or dealing with radiation spikes. AI astronauts will need to handle novel, unforeseen situations, diagnose problems they haven't been trained on, and make sound decisions without immediate human guidance from Earth.
That requires incredibly advanced perception, being able to accurately sense their surroundings in real time, despite challenging conditions like harsh sunlight glare, fine dust covering everything, extreme temperatures, or high radiation levels interfering with sensors.
And equally robust mobility and manipulation capabilities. For a robot, that means being able to climb over treacherous Mars rocks, use complex tools to diagnose and fix a faulty circuit, or carefully handle delicate scientific samples.
Getting around and actually doing things.
Right. It also needs sophisticated onboard cognitive architectures, the AI brain, that can process sensor data, reason about the environment and its goals, and make complex decisions on the fly, adapting its plans as needed.
Research efforts like NASA's work with Valkyrie and the development of advanced humanoid control software at places like IHMC, Institute for Human and Machine Cognition, are addressing the physical side of this. But the software, the ability for the AI to learn how to react safely and effectively to completely novel situations. That's key.
Using techniques like reinforcement learning, where systems learn through trial and error within defined safety boundaries, or extensive mission simulation to train for edge cases, that's where a lot of the cutting-edge research is focused.
Imagine an AI astronaut on Mars tasked with repairing a solar panel array after a dust storm. It might encounter a type of damage or a tool malfunction it's never seen before.
It would need to be able to diagnose the issue, perhaps look up information using its onboard knowledge base, figure out a workaround, and take corrective action immediately, all while managing its own power, health, and safety. That's something current systems simply aren't equipped to do autonomously across a wide range of possibilities.
A huge leap in capability needed there. The next required leap is achieving human-level communication and teamwork. An astronaut works as part of a cohesive crew, and AI astronauts will need to do the same, interacting seamlessly with humans or other AI systems and robots.
This goes far beyond simple voice commands or pre-programmed responses. It requires the AI to understand human intent, even when commands are ambiguous or informal. It needs to anticipate teammates' needs and communicate its own status, plans, and reasoning clearly and concisely.
Understanding nuance.
Exactly. Future AI assistants might even need to detect human emotion or stress levels through voice or biometric data and respond supportively or adjust their interaction style.
Like an AI noticing a crew member is clearly frustrated with a complex repair and proactively offering help. suggesting a different approach, or pulling up a relevant diagram without being explicitly asked.
Yes. And the sources note that culturally, astronauts already tend to treat robots like Astrobee or the Curiosity rover as quasi-colleagues. Achieving true teamwork means AI systems need transparency.
We need to know why it's doing something.
Precisely. Humans need to understand why the AI is doing something, to build trust and predict its behavior. NASA and others are developing explainable AI tools to show the reasoning behind an AI's decisions in a way humans can easily grasp.
Building that deep level of trust and mutual understanding between human and machine team members is absolutely essential for a safe and effective crew, especially billions of miles from home.
Absolutely. The third critical leap is developing truly reliable decision-making and learning. In the high-stakes, hostile environment of space, AI decisions have enormous, often life-or-death, consequences.
Like managing life support.
Managing the habitat's life support, navigating a treacherous landing, performing a critical repair in vacuum, or deciding how to react to a radiation flare. You simply cannot afford errors in judgment or unexpected behavior.
No room for error.
No. The brain of a reliable AI astronaut would likely need to be a hybrid system, combining incredibly robust rule-based logic for guaranteed safe responses in all known situations, essentially, hardwired safety protocols that can't be overridden with more adaptive machine learning capabilities to handle novel problems and learn from experience.
So,
Exactly. Encoding fundamental directives, like a space-hardened version of Asimov's 3 laws of robotics, ensuring that AI safeguards human life, obeys human orders unless they conflict with safety, and protects itself without conflicting with the first two is incredibly complex to engineer into software, but necessary to prevent unintended harmful actions.
ultimately, the initial and perhaps primary intended roles for these AI astronauts, at least in the near future, seem to be handling the jobs that are simply too risky, boring, or tedious for humans.
Precisely. The sources often categorize these as the 4 Ds: dull, dirty, distant, and dangerous.
Dull, dirty, distant, dangerous. Got it.
This includes tasks like habitat construction and assembly in harsh environments, mining ice or minerals in dark craters, performing lengthy external inspections or repairs, or conducting spacewalks in high radiation environments or areas with extreme temperatures.
Jobs humans probably wouldn't want anyway.
Maybe not. The sources include a powerful quote from NASA planning documents, painting a picture of this precursor role. The robot will get to Mars early, before any humans, and then be assistively teleoperated from Earth or later from orbit into assembling structures, so that everything is prepared for the eventual arrival of some weak and fragile humans.
Weak and fragile humans. That's quite a stark framing, isn't it? Puts us in our place.
It is, but it highlights the view that AI astronauts are seen fundamentally as enablers and amplifiers for human exploration. They pave the way, handle the foundational, risky, and monotonous work so humans can arrive into a safer, prepared environment and focus purely on the unique aspects of exploration and science that only humans can provide.
Like intuition, creativity.
Exactly, like intuitive geological fieldwork, creative problem solving, or experiencing the profound wonder of another world. They don't replace human explorers, they make human exploration possible, safer, and dramatically more effective.
And it's worth reiterating that AI astronauts in this vision aren't limited to humanoid forms like Valkyrie.
Good point. They could be AI co-pilots managing spacecraft systems, legged robots for traversing rough terrain, drones for aerial surveys or inspections, or even intelligent software agents overseeing base operations. The unifying theme is their advanced AI, enabling them to think, discover, decide, and act with significant autonomy, performing roles that were previously solely the domain of humans.
So function over form, really.
That's the idea. And the sources suggest that rapid developments in machine learning, advanced robotics, and human-robot interaction are accelerating our ability to bridge the gap between today's systems and this vision. Experts believe we will transition from mostly teleoperated robots to increasingly autonomous AI crew members with significant responsibility and capability in the next decade or two.
The next 10 to 20 years, that's soon.
Relatively speaking, yes. The extensive research, prototype development, and analog missions being tested today, from ESA's AI lab to NASA's exercises with robots in Mars analog environments, are all actively building these necessary skills and testing these concepts.
The image of the Valkyrie robot certainly serves as a powerful prototype representation of this vision, even if, as you mentioned, the software needs to catch up to the impressive hardware capabilities.
It does. So with the vision of the AI astronaut becoming clearer along with the necessary technological leaps, let's project forward. How do the sources see AI and these AI astronauts fitting into the concrete timelines being discussed for Mars exploration, specifically in the coming decades, the 2030s and 2040s?
Okay, let's paint a picture of the future Mars exploration scenarios based on the sources. AI is clearly poised to be absolutely instrumental in humanity's push to Mars. From the initial preparation missions to establishing a sustained human presence, it underpins almost every major step.
The 2030s are broadly framed as the era of robotic pioneers and intensive crew mission preparation. This phase builds directly on the autonomous robotic groundwork laid in the 2020s with rovers like Perseverance and Zhurong. It significantly intensifies this activity.
More robots, bigger jobs.
Pretty much. NASA's Mars Sample Return (MSR) campaign is a key example mentioned repeatedly as a high autonomy mission defining this era. It will feature a fetch rover or drones autonomously navigating across the Martian surface to locate and pick up sample tubes left by Perseverance.
Picking up the samples Percy left behind.
And critically, an ascent vehicle that autonomously launches those collected samples into Mars orbit for later retrieval.
That is an unprecedented level of autonomous operations on another planet for sample collection and launch, pushing the boundaries of what AI and robotics can do independently. By the early to mid-2030s, there's also the possibility, discussed in some sources, of a crewed orbital mission around Mars,
Potentially as early as 2033.
where astronauts fly to Mars but don't land.
Exactly. But from orbit, they could teleoperate AI robots on the surface.
Ah, so controlling them from nearby, relatively speaking.
Yes. With only hundreds of milliseconds of communication delay from Mars orbit to the surface, humans could control rovers, construction robots, or even early AI astronauts on the surface far more efficiently and intuitively than from Earth, which has that crippling 6 to 40-minute round-trip delay. This orbital phase would be a crucial dress rehearsal for human-robot teamwork before landing.
Makes sense. Practice before the big game. And the sources predict a significant influx of semi-autonomous robotic activity on the surface throughout the 2030s.
Yes, this means sending more advanced robots to begin building critical infrastructure like landing pads, robust enough for heavy vehicles like Starship, setting up solar farms for power, and assembling or 3D printing early habitat structures.
Building the first bits of the base.
They mention examples like concepts derived from NASA's Athlete rover or adapted industrial bulldozers. AI algorithms for multi-robot coordination, like ESA's CSRU project exploring cooperative ISRU operations, are under development to manage teams of robots working together on complex tasks.
China's ambitious plan to establish a fully robotic Mars research station by 2038 fits perfectly into this pre-human arrival phase.
It absolutely does. This is envisioned as an uncrewed base, using AI extensively for scientific research and, crucially, for ISRU techniques, like extracting oxygen from the CO2 atmosphere or water from subsurface ice. This robotic outpost is explicitly designed to demonstrate key technologies and gather data to prepare the site for eventual human visits.
Proving you can live off the land before you send people.
That's the idea. It mirrors their lunar strategy, where the International Lunar Research Station begins as a robotic base.
And then, by the late 2030s or early 2040s, potentially the first human footsteps on Mars. NASA's current target is around 2039 or 2040, which the sources describe as aggressive and audacious.
Aggressive sounds about right. This first crewed mission, whenever it happens, will be heavily reliant on AI support. The transit vehicle for the months-long journey from Earth to Mars, whether it's an Orion-derived habitat or a SpaceX Starship, will have to function largely autonomously.
The ship flies itself, mostly.
AI systems will manage life support, navigation, propulsion, and provide crucial medical and psychological support to the crew during the deep space transit.
And the landing itself, even with humans aboard, will use AI-driven radar and vision systems far more sophisticated than the Apollo computers to select the safest possible landing spot in real time while autonomously guiding the descent.
So the timeline for the 2030s looks like this. The first half involves intensive robotic groundwork and precursor missions. The mid to late 2030s could see crewed orbital missions refining teleoperation and human AI interfaces. And the late 2030s, early 2040s sees the first human landing, fundamentally enabled and made possible by all that autonomous robotic work that came before.
So the robots really do pave the way. And the first human mission won't just be humans, they'll likely bring their robotic crewmates with them, right?
Expect the first human crews to bring along updated robotic assistants, maybe a new version of Robonaut for internal habitat maintenance, or adapted legged robots like those tested by ESA in Mars analog environments.
Like spot the robot dog again.
Could be. for scouting terrain, carrying equipment during traverses, or inspecting external structures. These would act as direct robotic teammates supporting the human explorers.
Moving into the 2040s, the focus shifts dramatically towards establishing a sustained, perhaps semi-permanent human presence on Mars. And this requires a massive scale of construction, logistics, and maintenance, where AI becomes the absolutely critical workforce multiplier.
Exactly. Establishing and maintaining an outpost capable of supporting human life requires nonstop work. AI systems will become indispensable in daily operations, moving beyond just preparation to routine maintenance and expansion.
We'll see AI robots routinely performing EVA support tasks outside the habitat, handling complex habitat maintenance like fixing external structures, swapping out power units, or deploying scientific instruments.
Mostly solo, while humans supervise or step in for delicate, complex tasks requiring human judgment.
So the robots do the grunt work outside.
A lot of it, yes. Advanced robotics, potentially increasingly humanoid or specialized spider-like robots, could be tightening bolts on structures, fixing minor leaks, performing inspections, and deploying experiments across the base and surrounding area. AI will be coordinating complex ISRU operations, managing autonomous mining rovers extracting ice, overseeing AI-run chemical plants producing water, oxygen, and fuel, and controlling automated greenhouses growing food.
AI running the whole resource chain.
And swarms of smaller AI robots dedicated to base maintenance, cleaning dust off solar arrays, relocating equipment, inspecting utility lines.
With small human crews, perhaps just 6 to 12 people at a time initially, they will rely incredibly heavily on these automated and AI-powered systems for their survival and productivity.
The sources suggest each astronaut might have multiple AI assistants, some physical robots, some software agents to offload tasks and provide support.
Like a geologist astronaut going on a traverse miles from the habitat,
Yeah.
accompanied by a robotic field assistant that follows them, carries their heavy tools, documents the site with cameras, and collects samples under guidance.
That exact scenario has been tested in analog environments, like the Analog 1 experiment where an astronaut on the ISS remotely guided a rover in Italy for sample collection.
Right.
On Mars in the 2040s, the difference will be the human astronaut is right there on the surface giving direct commands, and the robot's onboard AI handles the low-level tasks like navigating around a tricky boulder field or executing the precise movements needed to drill a sample, while the human focuses their cognitive energy on the scientific observation and decision-making.
The human does the thinking, the robot does the doing. AI will also be crucial for mission management on Mars itself, acting as a local mission control or the mission ops brain for the base, because real-time support from Earth is still impossible.
This AI system would be consolidating telemetry from all base systems, flagging potential issues using diagnostic AI, optimally scheduling activities for robots and humans, managing power loads, and coordinating communications, essentially an AI version of NASA's Class P ground software, but operating autonomously on Mars or aboard the habitat.
The base basically runs itself with AI oversight.
To a large extent. By the end of the 2040s, the sources envision potentially a small, growing village, maybe an international base with interconnected modules, and a central AI could function as the base computer, perhaps like Tony Stark's Jarvis in fiction.
Jarvis on Mars.
Controlling the entire environment, managing communications, interacting with crew members via natural language interfaces, and serving as a repository for all base knowledge and procedures. In an emergency, like a suit issue during an EVA or a sudden dust storm forcing an evacuation, an AI companion or base AI might be the first to detect the problem, offer solutions, or automatically call for help.
A crucial safety function. And the private sector's vision, particularly SpaceX's Starship colony plan, could accelerate this robotic buildup phase dramatically. Their concept involves sending dozens of cargo starships to Mars, carrying vast quantities of equipment and autonomous machines to rapidly bootstrap infrastructure before the first people arrive.
Elon Musk has spoken about fleets of cargo starships deploying AI-powered robots to set up solar arrays, build landing pads, establish propellant production facilities, and assemble habitat modules. An AI robot army, if you will, tasked with making the base semi-operational and survivable before humans even step foot on the planet.
So the picture for the 2040s is one of increasing permanent presence, where AI systems are not just helpful, but absolutely indispensable in daily operations, survival, and expansion. It's a complex, highly interwoven dance between human astronauts and their increasingly intelligent and capable robotic and software counterparts.
NASA's goal of humans on Mars by 2040 is described as aggressive and audacious, but the sources state it's anchored by the requirement for significant technological advancements, and AI autonomy and capable robotic systems are right at the top of that list.
Meeting that goal heavily depends on how capable our AI and robotic systems become, whether they can reliably construct, maintain, and troubleshoot systems, and partner effectively with human crews. If AI astronauts mature and fulfill their envisioned roles, the odds of success for establishing a sustainable presence increase dramatically.
By the late 2040s, the sources suggest the line between human astronaut and AI assistant may blur as closely integrated teams of humans and intelligent machines operate cohesively on the Martian frontier, pushing the boundaries of exploration together.
This future holds incredible promise, allowing us to do things in space that were previously confined to our imaginations. But deploying this kind of advanced AI in deep space brings not only huge benefits, but also significant technical hurdles and crucial ethical considerations. It's a landscape of complexities and trade-offs we absolutely need to navigate.
It certainly is. Let's weigh those factors. The sources detail several key advantages offered by incorporating AI astronauts into missions.
The first, which underpins much of the vision, is enhanced mission efficiency and capability.
AI agents can work around the clock without fatigue, accelerating the pace of operations on a planetary surface or within a habitat. While humans need to rest, sleep, and eat, a solar-powered AI rover can keep exploring, or an AI system can keep monitoring equipment and processing data 24/7.
Robots don't need sleep.
Nope. AI can also multitask. An AI system could simultaneously monitor life support systems, control a science experiment, and navigate a remote rover, effectively augmenting the human crew size without needing extra life support, food, or space.
The AGIS system on the Mars rovers, by autonomously identifying science targets and cueing instruments, dramatically increases the amount of scientific data collected compared to relying solely on human operators to review images and send commands every day. That's a concrete example of AI directly increasing efficiency and science return.
Yes, AI can maximize every available minute and resource, from performing routine system checks to executing complex mapping or maintenance tasks in parallel with human activities.
Perhaps the single most critical practical advantage, especially for missions beyond the moon, is providing essential autonomy in the face of communication delays.
Absolutely. With the 6 to 40-minute round-trip delay to Mars, real-time remote control from Earth for many critical tasks is simply not feasible or safe.
You just can't wait that long for instructions.
Exactly. An AI astronaut or AI-powered system on the ground or onboard the spacecraft can make instant decisions. A rover detecting and avoiding an unexpected hazard like a sudden drop-off in milliseconds, or an AI medical system analyzing an astronaut's condition and guiding a procedure in real time when ground support is many minutes away.
This capability provides essential self-reliance for the mission, allowing operations to continue smoothly and safely even when cut off from timely communication with Earth. The sources call this capacity for autonomous action especially vital for missions to Mars and beyond, where the tyranny of light speed becomes a major constraint.
Another major advantage is significant risk reduction and safety improvements. AI robots can take on the tasks that are simply too dangerous for humans, the 4Ds: dull, dirty, distant, or dangerous.
Those 4Ds again. Like exploring the floor of a high-radiation crater, performing external repairs or inspections in the vacuum of space or during a solar flare, or venturing into unstable lava tubes or icy caverns.
Exactly. You send the robot or the AI drone instead of a human. AI systems don't require oxygen, aren't susceptible to radiation damage in the same way humans are, and their loss, while costly, isn't a loss of human life.
Disposable in a sense compared to a human life.
In a harsh sense, yes. In emergencies, AI might react faster than humans automatically isolating a habitat breach, deploying countermeasures during a solar particle event, or executing an evasive maneuver to avoid a collision. By acting as a first line of defense and performing these hazardous jobs, AI systems significantly improve the overall safety of human explorers. They can function as trailblazers and guardians in the most dangerous areas.
AI can also dramatically increase our science and exploration reach.
Yes. A human crew might be limited in the range they can explore from their base due to travel time and life support constraints. An AI rover or drone operating autonomously could explore hundreds or thousands of kilometers away as a proxy geologist or scout, venturing into areas too far or too risky for human boots.
Covering way more ground.
Way more. AI also directly helps in scientific analysis itself, as we discussed with the Rosalind Franklin rover's ML algorithm speeding up the detection of organic molecules, ensuring scientists get the most out of the data collected.
It essentially extends human senses, intellect, and limbs across a wider area. Imagine a network of AI-powered seismic sensors across the planet, or AI drones mapping complex cave systems that humans can't access. The result is a much richer and more comprehensive scientific return from exploration.
Operational support and cognitive offloading is another key benefit, focusing on supporting the human crew directly. Human astronauts on long, deep space missions will face significant workloads, high stress, and potential isolation.
Yeah, it's got to be tough mentally. AI companions and systems can provide both technical and, perhaps in the future, emotional support.
Technically, AI can act like an expert consultant for the crew troubleshooting complex systems by cross-referencing manuals and telemetry, offering suggestions drawn from vast knowledge bases, monitoring schedules, providing reminders for critical tasks like water intake or equipment checks.
Like a super smart checklist and troubleshooter.
Exactly. Psychologically, AI companions like Simon or future systems designed to understand emotion and engage in more natural conversation could potentially help mitigate loneliness, boredom, or interpersonal conflict by providing companionship or distraction. The sources specifically highlight that AI assistants could offer valuable psychological support on long, isolated Mars missions where traditional human support networks are distant.
Resource optimization is another critical area where AI excels and is essential for mission longevity.
Managing complex systems like life support, power grids, propellant levels, and consumable stores on a self-contained Mars mission involves countless interdependencies and parameters. AI can juggle all of these factors in real time to optimize resource use.
Squeezing every drop of efficiency out of the system.
Pretty much. Adjusting the habitat thermostat based on occupancy and power availability, scheduling power-hungry tasks when energy is abundant, rationing consumables like water or oxygen in an emergency scenario. It acts like a smart facility manager for a Mars base, maximizing the efficiency of every single resource, which is absolutely vital for mission endurance far from Earth.
And finally, AI can enable entirely new mission concepts that weren't feasible before.
A fully autonomous mission carried out solely by AI robots could be sent to destinations too risky or challenging for humans in the foreseeable future, like the surface of Venus or the subsurface oceans of Jupiter's moons, paving the way for future exploration.
Going where no human could realistically go.
Right. AI could also allow smaller human crew sizes for expensive Mars flights by offloading work onto automated systems, or even enable concepts of uploaded AI avatars of astronauts operating complex robots on the surface remotely before the human body arrives, a blend of telepresence and advanced autonomy.
So AI adds incredible flexibility to mission design and opens up entirely new frontiers for where and how we can explore.
However, as you mentioned, these significant benefits come with significant challenges and technical hurdles, especially given the unique and incredibly demanding space environment.
Perhaps the most fundamental challenge is ensuring AI reliability and robustness. Space is unbelievably unforgiving.
It is. Hardware fails, and it's incredibly difficult to repair billions of miles away. Software bugs, which are common in complex AI systems, can be mission fatal. AI systems must function flawlessly under incredibly harsh conditions, extreme radiation that can flip bits in computer memory, vast temperature fluctuations, and the vacuum of space.
That radiation is a killer for electronics.
It really is. The high-performance processors needed for advanced AI are often particularly sensitive to radiation. Developing radiation-tolerant AI hardware is a major engineering challenge in itself.
And it's not just hardware. The AI software has to handle unexpected situations that weren't in its training data. If a rover AI encounters something completely novel and makes a wrong decision, there's no immediate human fix available with that communication delay.
Exactly. NASA and other agencies place immense emphasis on extensive testing and verification for all plausible scenarios. But achieving human-level adaptability in novel situations while maintaining machine-level reliability across a vast range of possibilities is called a tall order by the sources. Systems simply must keep running without problems for potentially years, which is incredibly difficult to guarantee with complex learning AI.
Another critical hurdle is balancing autonomy versus control. How much freedom do you give an AI astronaut?
This is a very complex issue. If you give the AI too little autonomy, you lose the benefits of real-time decision-making and offloading tasks. But if you give it too much autonomy, you risk the AI taking undesirable or even dangerous actions because it lacks human common sense, understands the situation incorrectly, or its objectives aren't perfectly aligned with the mission's safety requirements.
You don't want HAL 9000 opening the pod bay doors.
That's the classic fear, isn't it? You need to build in robust constraints and fail-safes. A habitat AI should never, ever shut off life support to save power, no matter how logical that might seem from a purely energy optimization standpoint.
Like needing a space-hardened version of Asimov's laws
Mhm.
that you can absolutely rely on the AI to follow.
Yes. Agencies like NASA are developing responsible AI principles that emphasize transparency and accountability. An AI agent must be able to explain why it made a particular decision in a way humans can understand, and there must always be protocols for human override when necessary.
Explainable AI, that seems key for trust.
It really is. Techniques like explainable AI and sophisticated supervisory control interfaces are being researched. Building trust with the human crew is also essential if an AI makes a questionable call. Clear protocols for human intervention and regaining control must be ingrained. Designing AI that is smart and capable enough to act independently, but humble enough to defer to human judgment in critical situations, is a significant new frontier in human factors engineering for space.
Limited computational resources are another significant constraint in space compared to Earth.
Advanced AI, especially deep learning algorithms used for complex image recognition or decision-making, is computationally intensive, requiring significant processing power, memory, and energy. Spacecraft and future Mars bases have tight limits on weight, energy consumption, and heat dissipation.
Because every watt and kilogram costs a fortune to launch.
Exactly. Running complex AI like real-time image processing for autonomous navigation or a large language model for crew interaction is challenging on onboard hardware with these constraints. Engineers need to develop highly optimized algorithms and specialized radiation-hardened AI accelerator chips.
And retraining complex ML models on Mars without access to Earth's massive cloud computing infrastructure is also difficult.
Right. It requires developing efficient online learning methods or relying on periodic updates from Earth. Also, AI must function effectively even with limited bandwidth back home, meaning it needs to process data locally.
Unpredictability and verification are also major challenges unique to complex AI systems.
AI, especially learning-based systems, can sometimes behave like a black box. It might produce unexpected behavior in novel situations not explicitly covered in its training or testing data. Verifying and validating AI systems to the extremely high reliability standards required for spaceflight is much harder than for traditional deterministic software.
Where you know exactly what it will do in every situation.
Exactly. Space mission managers traditionally prefer systems they can exhaustively test and understand completely, which clashes with AI's adaptive and sometimes unpredictable nature.
This might lead to a more gradual, phased approach, starting with AI in advisory roles before moving to semi-autonomous and then fully autonomous control for critical functions.
Exactly. Verification relies heavily on extensive simulation across a vast range of scenarios, but there is always the risk of unknown unknowns encountering a situation that was never anticipated. AI systems need to exhibit graceful degradation if they encounter something they don't understand or a system anomaly. They should alert humans and go into a safe mode, not take random or potentially harmful actions.
Fail safely, basically.
That's the goal. Ensuring AI goals are perfectly aligned with the mission's overall safety and success is paramount. All these technical challenges contribute to very high development and testing costs for flight-ready space AI.
Finally, interoperability between different systems from various agencies and companies becomes a significant hurdle in a multinational or multi-company Mars-based scenario.
If NASA's Habitat AI needs to communicate with ESA's Rover AI, coordinate with China's ISRU robots, and interact with the SpaceX lander's computer for refueling, making all these diverse, complex systems work together seamlessly, efficiently, and securely is a non-trivial engineering challenge.
Getting everyone's AI to play nice together.
Common standards and protocols for space AI interfaces and communication will be necessary, requiring significant international coordination, potentially extending existing frameworks like CCSDS, the Consultative Committee for Space Data Systems.
Beyond the technical, there are crucial ethical and policy considerations raised by deploying AI agents capable of independent action in deep space, particularly when they're integrated with human crews.
These are fundamental questions that ethicists, policymakers, and engineers are grappling with. Crew safety and moral responsibility are paramount. If an AI makes a decision that directly leads to an accident affecting human life, who is accountable?
The programmer, the commander, the AI itself.
Exactly. Is it the developers who programmed the AI, the mission commander who relied on it? Or is the machine itself somehow accountable? Ethically, AI decisions that impact human safety must be transparent, and the ultimate authority and accountability need to reside with humans. Thorough testing is not just an engineering requirement, it's an ethical obligation when human lives are at stake.
Decision autonomy in life-critical situations is a major point of discussion. Should an AI medical system have the authority to recommend or even execute a risky treatment procedure that a human crew member disagrees with?
This raises complex questions about consent and authority. The sources suggest that in situations involving human life or irreversible actions, the ultimate decision authority should likely remain with the human crew or accountable ground control, even if the AI provides the recommendation.
The human has the final say on their own life.
Essentially, yes. There's a clear need for AI ethics guidelines embedded in mission protocols, ensuring AI doesn't make critical decisions about human life without informed consent where possible. The concept of human in the loop versus human on the loop governance becomes crucial. Humans should at least be on the loop, understanding what the AI is doing and why, and able to intervene if necessary, which respects human agency and responsibility.
There's also the philosophical question of replacement versus complementation of human roles.
Mhm.
Will increasingly capable AI eventually replace human astronauts entirely, or will they simply assist and augment them?
Space exploration has profound human significance: the drive to explore, the unique perspective humans bring, and the inspiration human presence provides. Most sources frame AI as augmenting human capabilities, enabling humans to perform the uniquely human tasks like complex scientific reasoning, intuitive geological fieldwork, creative problem solving in novel situations, and inspiring humanity back on Earth by being there.
So AI helps humans do the cool stuff.
That's the optimistic view. However, if future AI systems made uncrewed missions vastly cheaper and safer than human ones, it could spark significant ethical debates about whether sending humans to risky environments like Mars is still justified. Most sources emphasize that the human experience of exploration is irreplaceable. An ethical benefit often cited for AI is precisely that it reduces the risk to human explorers by taking on the most dangerous jobs.
The emotional and psychological impacts are also incredibly important when integrating AI into the small, isolated environment of a space crew.
Crew members might form strong attachments to AI entities they work with closely, similar to how rover teams personify their robots.
Like naming them and talking to them.
Exactly. An AI malfunction or unexpected behavior could cause significant distress or anxiety in an already high-stress environment. Privacy is also a concern. An AI companion that is always listening for commands or monitoring crew health data could feel intrusive. Clear boundaries and consent protocols are needed, analogous to having mute buttons on smart home devices. The AI should be programmed to respect crew privacy and consent regarding data collection and interaction.
And how do we treat the AI? Especially if it seems quite human-like.
That raises questions about interpersonal dynamics, codes of conduct, and treating AI team members with a certain level of respect, even if they are tools.
There's also a significant risk of over-reliance and skill degradation for astronauts.
If AI handles all the complex tasks, navigation, troubleshooting, system monitoring, decision-making, astronauts might lose proficiency in these critical skills. This becomes incredibly dangerous if the AI system fails, leaving the crew unable to take over manually.
Like pilots losing stick and rudder skills.
Exactly. It's analogous to pilots losing manual flying skills due to over-reliance on cockpit automation. Mission planners must balance the benefits of automation with the need to keep the crew engaged, trained, and proficient enough to understand the systems and take over manual control if necessary. The principle of meaningful human control is vital here. Humans should maintain sufficient understanding of the situation and the AI's actions to intervene effectively if needed. This is important for both safety and maintaining the dignity and agency of the human crew.
While still largely theoretical for the kinds of mission AI being developed now, the sources also touch on the philosophical edges of AI rights and treatment for potentially very advanced future systems.
Yes, some ethicists and AI researchers muse about whether highly advanced, potentially sentient AI agents in the far future should be granted some form of moral consideration or rights. This is well beyond the scope of foreseeable Mars mission AIs, which will be designed and used as tools.
We're not talking about sentient AI crewmates yet.
Yep. Not yet. But future speculation could raise questions about, for example, the ethics of sending a sapient AI on a one-way mission to explore a distant star system. For the next few decades, ethical treatment of space AI primarily means aligning their design and use with human values, ensuring they are safe and reliable, and not causing harm through poor programming or oversight.
Finally, there are important policy and legal issues that need to be addressed as AI in space becomes more sophisticated.
Using AI in space might require new regulations. For example, who is liable if two autonomous satellites controlled by AI systems miscalculate trajectories and collide in orbit? Existing international space law, like the Outer Space Treaty, often assumes human control and national responsibility for space objects. This may need updating to account for AI decision-making.
The laws weren't written with AI in mind.
Not really. Establishing AI norms among nations could also help prevent misunderstandings or escalations, similar to ongoing discussions around autonomous weapon systems, although the application is different. Collaborative international groups are needed to establish common standards and best practices for the development, verification, and safe deployment of AI in space. Transparency about the algorithms and decision-making processes used in critical space AI systems could even become a factor in international mission diplomacy and cooperation.
So the deployment of AI astronauts and advanced autonomous systems in interplanetary missions presents this incredible complex landscape of trade-offs. On one hand, there are huge potential rewards in terms of dramatically increasing safety, scientific discovery, operational capability, and enabling human exploration of destinations like Mars that weren't truly within reach before.
And on the other hand, we face significant technical challenges in achieving the necessary reliability, navigating the complex balance between autonomy and human control, dealing with limited computational resources, verifying unpredictable AI behavior, and ensuring interoperability between diverse systems.
And woven through all of this are the crucial ethical questions we must grapple with: accountability, safety, the fundamental role of humans in exploration, the psychological impacts of AI crewmates, the risk of over-reliance, and what standards we set for these intelligent systems.
Addressing all of this effectively requires a genuinely interdisciplinary effort, not just engineers building the AI, but ethicists guiding its use, psychologists understanding its impact on crews, and policymakers creating the necessary frameworks. And the sources consistently emphasize that throughout all of this, humans remain at the center of space exploration.
Yes, as the drivers of the vision, the leaders making the ultimate decisions, and ultimately the ones whose experience and presence gives exploration its profound purpose, AI augments. It doesn't replace the human desire to explore.
The path to Mars, and indeed the path to exploring deeper into the cosmos, looks like a fundamental partnership between human astronauts and their increasingly intelligent robotic and AI counterparts. The first human step on Mars might truly be a human-machine team achievement. Ensuring this team operates safely, ethically, and effectively will be a defining challenge in writing the next chapter of human and AI space exploration.
As we send increasingly capable AI into the cosmos alongside human explorers, enabling us to go farther and do more, what does that evolving partnership teach us? Not just about Mars and the technical possibilities of spaceflight, but about our own definitions of exploration, intelligence, and what it truly means to be a crew pushing the boundaries of the known.